in this presentation, I just thought I would talk about the data science outlook, machine learning, deep learning, generative AI for 2024, but this will be sort of like starting, from somebody transitioning from school to, the workplace. So, see, hang on. All right, it won't let me. Oh, there we go. All right. So I think great place to start is the history of AI and machine learning. So a rise of computing power is key, right? So a lot of these algorithms, they've had since the 50s, like deep learning algorithms since the 50s, but they didn't have the computing power to basically realize it, right? So if you look at the 80s, office computers were not really popular before 1980. And even in 1980, maybe like one person had a computer in their whole office, maybe a few people, maybe just IT staff. Really, we're talking about the 90s, where that's when like everybody had a computer, right? So, to where it's like, a personal computer was really popular. Till then, you couldn't even do computing. So where would you run algorithms, or where would you run data science? There was really no, concept of data science unless it was like IBM or something like centralized, right? And the 1990s was the era of relational databases. So this is when everybody, the IT department would have a huge database, and then that you try to put everything in the kitchen sink into that database, but you didn't know what to do with it. Then the 2000s, late 90s, 2000s, this is the era of big data and data analytics, right? So they got all the data into databases. Now what do you do with it? Right. So you had to have some kind of BI, data analytics. So that's kind of a separate world on its own. We're going to talk about all these things. And in 2000s, I would say right around this time, machine learning was viable around maybe about 2005, 2008, probably, because at the time, machine learning was only taught in as like a grad school, or like a PhD, classes. It wasn't really available to everybody. Remember the internet when it first came, right? It didn't have all the information that we have today, right? So even though it was there was very little information. This type of machine learning stuff, like today, you can just find information on anything, right? It wasn't really there around that time because, like I said, it was only available for graduate or PhD students. 2010s, I would say this is when, deep learning hit it big. And then Gen AI, deep learning is, of course, 50 years old or older than that, to where, people just try to model the brain, and then come up, model the neuron of the brain, and see if you can, do computing with that, right? And that's been popular. Now in the 2020s, large language models, and then Gen AI has become, common buzzwords. So the whole key to the slide is that without the rise of computing power, I'm also, electrical engineer. That's actually what I went to school for, and I switched to data science. But packing more transistors in the chip, right? That's really what caused the boom in data science, because now the computer became more portable, right? The computer became more accessible. Now you could run these algorithms which previously you couldn't run. One note I would say, remember in the 50s, computers were like as big as this room, and you basically had to run like instructions through tape, right? You can find those videos on YouTube. So that's how it was, to where you didn't even have memory storage. You had like tape, which punched out instructions. So we've come, from that to where we are here. So the other thing, next slide here, I want to say is that data science is multidisciplinary. So what this means is that people come into data science from different majors. As you guys know, computer science, right? Data scientist role actually came from here. It's basically, like I said, like a CS major, really came from, a master's program or PhD program, the machine learning. Then there are people that come from statistics background, right? This is your traditional statistics background, right? Then you have people coming from IT, database, and then ETL, extract, translate, load. These are the people that, kind of like the data engineering. Today we call this data engineering, but these were the guys that did data analytics. So then you have data analytics guys, business intelligence. This is overlap with IT staff. And then you have a whole slew of people coming from business, economics, econometrics, actuarial. Actuarial is usually like, in the insurance kind of industry. They try to figure out, how long, a person how long a person's going to live so that they can sell them insurance. And then also clinical psychology, public relations, and a lot of other fields. So today it's kind of, populated with people coming from all these disciplines, not just computer science, right? An example of that would be me, coming in from electrical engineering to do this, right? So, okay. So some of this is going to be humorous. So I'll talk about different things here, job outlook. And, today everybody's a glorified data scientist. It's my opinion. So this is vastly different from the original data scientist. So the original data scientist, like we already talked about, you had the data scientist role. Today it's everybody. It's the original data scientist. Today it's someone doing like statistician type work, someone doing ETL type work, right? Heavy SQL lifting. We'll talk about this in a bit. And then a data analyst that does Excel, Power BI, SQL, a business systems analyst, sometimes, data quality governance staff, fringe data science staff. These are like marketing people or, literally anyone that knows some Excel, SQL, or is data savvy. So the reason I put the slide in here is that all these people are sometimes called data scientists. So when you get a job, you don't know where you're going to go here. So that is, that was kind of a shocker to me in that people that work in IT that do heavy data engineering, right? Those people are also sometimes called data scientists. Now the name has been sort of polluted with basically all these tasks. So you could go in there thinking you're doing one thing, and you may just be doing like, reporting or something like that, right? Okay. So following that, data science is a catch-all today. So what that means is that, just like I said, generally all of these tasks are under data science, and you do not know what you'll be doing. Job descriptions are seldom accurate. So modeling, right? This is what everybody wants to do. The chances of landing this job exclusively is rare. I'm still trying to find that perfect job where I just model and that's it, right? It's pretty rare. It's even if you get a job like that, right? Uh, it's really rare that they're just going to give you the data that's already made up and then you just run models. They're out there, but there's a lot more competition, right? So data engineers may help, but you still have to do SQL, right? You still have to do some amount of SQL. Uh, Sometimes data engineering, data prep. So getting the data right is a bigger deal to managers. Like I work for companies where that's all I care about is just the data. And then, they think that you're a data scientist if you're like a SQL star, if you know all the SQL stuff. So the thing with SQL is that you don't really need a degree to do that. So all these things like data analytics, uh, data analysis, right? And SQL, a lot of the IT staff, they don't have like a CS degree or they don't have, so you're kind of thrown in there with people from, all over the place. So unfortunately, that's the truth. And then usually 70% of your work will usually be SQL in a normal, company, which I'll talk about in the next slide here. So a lot of times, you're not going to get to do like all the cool stuff all the time. Like I said, I'm still looking for that ideal job where, you just get to do the modeling and the cool stuff. So, and then you have BI dashboards reporting. So all these things are kind of under data science. So if you get a data scientist job, you'll be doing some modeling, a lot of data engineering, probably, BI work, dashboards, reporting. So you will most likely not land a modeling only gig, right? Which is just the truth. Only a few people can land that. So then we're going to talk about democratizing machine learning, the rise of cloud auto ML. So circa 2000s, data scientists had to have a PhD in computer science because that was the only place where it was taught, right? So with auto ML, which means, automatic machine learning, right? This is just to where it takes care of all the, parameter tuning, it takes care of everything. You just load the data and then it just, spits out the results of a model. So with auto ML, any high level manager or a marketing person can generally load data and run models. So I think it's no longer special. One thing I want to say, guys, I can't see the comments, so you'll just have to give them to Jason. So I'm just seeing my screen right now. So a funny joke that I like to make here is that Google calls this cloud ML effort democratizing machine learning for everybody. I call it putting data scientists out of work. So thus the modeling effort is really only 10 to 20% of the job. Some 80% of the job is usually getting the data right. when we say getting the data right, this means getting the data from different sources. It might be from different, databases. You have to put it together and stitch it together. Now, if you're lucky, you'll have a data engineering team, which you can just say, hey, I want this data, and they'll do it for you. So I've been in all these kind of jobs. I've been in a place where I can just sit there and model, and, and I have data engineers, and then they'll put the data together for me, but it's really rare, or they're so backlogged that they can't do it right in a timely manner. So you got to roll up your sleeves and get in there. So most of these jobs, they'll have like a SQL component where they ask you about SQL, and sometimes ultimately that's all it's about. Unfortunately, uh, passing that SQL exam. But most non-technical data scientists will say things like the modeling is the easy part. Now, of course, this is a kind of a misnomer, but these are the people, I would say the people that aren't focused on modeling itself. And like we talked about, it's just 10 to 20% of the work where if you load it into AutoML, it will just almost anybody can just run a model and then, get results, right? So you will get this kind of stuff that modeling is the easy part. So to me, when somebody says that, they don't understand modeling, right? They're probably coming from the data engineering world, or they think that it's all about the data, getting the data right, which is true. It's all about the data because once garbage in, garbage out, right? But the modeling effort is crucial. If you don't know what you're doing, the models aren't going to be as good, right? All right. So having said all this, there are generally two types of companies, right? So this is key to understanding the scope of jobs that are available for anybody, graduating or, then maybe even that's already in the business, like me. So type one, I like to classify this as type one and type two, right? Type one is just a general business. Some 70% of data scientist jobs, or just data science in general, are usually from type one. So these are the kind of companies that they require some modeling, some data science work. Modeling will be basic, but the problem is non-trivial. So let me explain that statement because it sounds kind of contradictory, right? So usually with general businesses, they're usually asking you to just predict something, right? Usually it's like something like sales or something like profit or some kind of outlook. So these things are non-trivial. These are some of the hardest problems to predict because they're kind of real world problems, right? So they're highly nonlinear and they have a lot of exogenous variables that you don't even know what they are. So we'll talk about this in the coming slides, okay? And then type two, these are the heavy lifters that do the cutting edge work. So this is where you actually do machine learning type work. These companies tend to be high-tech companies, like maybe like your Facebook, Google, a lot of other companies that are actually using this, technology to build something new, rather than just using it for, okay, wait, make me a prediction, right? And usually, like I said, 70% of the jobs are like that, to where you just go into a company and they just need some kind of predictive help. And that's why they hired you, and that's pretty much it. You're not going to be doing something too exciting. It's just same stuff again, over and over again, which is just like, okay, predict sales, predict it, next month's customer, churn or things like that. So the competition is very high for these type two jobs. So type one, type two is where everybody wants to be, but the competition is very high, right? Okay, so data science, I would say, has gone niche, right? So unless you're highly specialized, data science can be generic, just like I've been talking about. Generic meaning that, okay, wait, just make a prediction for something, right? It's just a common metric that they're trying to, get you to predict. So these are specific applications of data science. Of course, there's a lot more. Natural language processing, NLP, computer vision, Gen AI, and LLMs now, right? But actually, LLMs have been around for 10 years or more. I've been in that space for over 10 years in the chatbot space. So now everybody knows about it. But these are some specialized fields. The problem here is that you'll have to invest your entire career in one thing to get good at it and get jobs, right? So if you have no experience in computer vision, they're not going to hire you for a computer vision job. If you have no experience in NLP, they're probably not going to. So it's really hard to get into these kind of jobs. These are basically type two jobs, right? So it's really hard to get into this kind of specialized job because they require a lot of experience. You already have to have been doing that to get in Okay, these jobs are harder to get, high competition and requirements, right? Um, let's see. Okay, so we're going to shift gears a little bit and talk about different things here. So deep learning is usually overkill for normal companies, like type 1 companies, right? So deep learning usually requires lots of training data and training time, right? And typically this is in type 2 companies, and it's used for things like computer vision, NLP, pattern detection, fraud detection. But as in data science, you know that there are many solutions to one problem. So deep learning may not be the preferred, option for fraud detection, because one of the key things here is that there's this notion of how computationally expensive something is, right? So you don't want to put a deep learning solution if it's not really needed, because any solution that you deploy has to be sort of lightweight, lean and mean. You know what I mean? So best use of deep learning in type 1 companies that I've seen is usually time series forecasting. Requires less data than traditional statistical models. But time series is so common that there are other options beside deep learning. So if you have a deep learning solution that's, totally time consuming, resource hogging, it may not be the best solution, right? So you may get pushback using deep learning from type 1 companies because deep learning offers no explainability, and it's usually more opaque than machine learning. So we will talk about this in a bit. Sorry, I have this. I need to move this out of the way. Okay, so I couldn't see that last statement here. So most of the time, machine learning ensemble models will outdo deep learning in most cases. So ensemble models are really they seem to be doing all the heavy lifting, except most of the time in type 1 companies, right? Okay, so the saturation of data science. So I think this is important. This is probably the most important slide, I think, besides, anything else that's technical here. But saturation occurs when there are more participants than available slots, because a particular field is booming and very popular, right? So currently, data science is producing more and more graduates. So there are more people looking for jobs than there are jobs. And I think that's the truth here. So a typical job can get anywhere from 300 to 600 applications. So that is a lot of applications for a single job. And LinkedIn actually stopped showing the exact number of applicants recently. Now it just says over 100 applicants. Before, it used to actually give you the exact number. So what they're trying to do is that if people see, and this shift just happened a few months ago. So if people see that 500 people have applied for this job, right, you may be like, you may give up and not apply. So nowadays they just say over 100. So when it says over 100, you can bet that it's probably, a lot of jobs. There's some jobs where, almost 1,000 people have applied. So think about the chances that your resume is going to land on a hiring manager's desk when you have 1,000 people that are competing with you. So job hunting, I would say, is now a hobby. But what I mean by that is that everybody's looking for the next opportunity. I think that's the new culture, right? So I would say almost everybody is kind of looking for a job all the time, right? Somebody might forward something to them, or they're just kind of looking, or, typically people don't stay in a job for more than, a year to like 3 years. And, that type of job hopping is very common today. So, like I said, everybody's always looking for a job. Solutions to this, there are none. You got to get good at networking. I mean, how are you going to compete with, 600 people, right? Or even 300 people? Uh, so you just have to get good at networking. Like I said, that's why I'm saying there's a saturation here, to where just recently, I would say within the last year or so, right? You're getting, a lot more people looking for jobs and people, their actual jobs available. And then you have people that already have jobs looking for jobs, because job searching is now a hobby. In a lot of ways, that's the only way to get a raise today, easily, or, substantial raise, is because, you might get like a 10% raise if you go to the next job, right? So people are constantly looking to, in the old days, people used to stay in a job for 15 years, 10 years, right? Now, I think if you do that, future employers might look at somebody who's put 15 years in one position and say, well, his experience isn't diversified. So it's a different way of thinking today. Okay, so let's get back into what machine learning can do. Machine learning cannot really solve a lot of problems, solve all problems, right? So part of the hype of machine learning is that it's a silver bullet. So I'm going to say this is simply not true, because it's only as good as the data that goes in, right? So models can help you make informed decisions. That's probably the only truth. Models and data can make you, help you make informed decisions. So machine learning is simply like newer computation techniques based in computer science, right? That give more accuracy over traditional statistical methods. So that's really all it is, for the purposes of prediction, right? So if the target variable is not correlated with the features in some way, no amount of machine learning magic will give any meaningful results. So a lot of times managers don't understand this. We'll talk about that in a bit. And machine learning will not work well in a nonlinear problem space for predictions. It can work, but like I'm saying, it's not really going to work well, right? If the problem is nonlinear, for example, for something like, okay, predict the price of gas, right? You don't even know what the variables are that go into making that prediction. You don't have control over those variables. You don't have the data source to put that stuff, into your model. You don't even know what those variables are, right? It could be something like, the president having a fight with the Middle East, then, gas prices go up. So these kind of things are highly nonlinear to where they're not really correlated to anything. So correlation is important to have any kind of predictive power. I mean, most of these problems are basically, linear. We'll talk about linearity, right, in a bit. So managers, so typically accuracy for general machine learning models for things like sales, spend, like I said, type 1 companies, these are the kind of problems you're going to get, will usually only be 65 to 75% due to too many exogenous variables. Like I said, that you don't have data for, you don't even know what they are, right? So your model accuracy will usually be about 65% to 75%. Anything more than that, you've probably done something wrong, like, have some kind of data leakage, or, the classic mistake that every rookie makes is that they feed they feed the target variable in with the training data. So, and it comes back with like 99% accuracy. Everybody makes that mistake. I've made that mistake, I'm sure, that's a point for everybody to be like, So managers will keep pushing for high accuracy because they don't understand this process, right? Somebody that doesn't understand data science and machine learning is going to say 75%. That's not that much. And you have to remind them that for this type of model, this is pretty good. For something like predicting, what might the spend be, which is a reaction to the market, right? Which you have no control over. This is about as good as it's going to get, right? I remember a manager telling me, he was joking, but this was still funny, that he goes, when Karthik gets this model to be 99% accurate, I'll be happy. And, of course, that's basically impossible to do for these type of problems, because we're not dealing with basically, deterministic problems, right? So we're not dealing with anything like, like image classification. Now, in something like that, that's different. You'll get 99% accuracy. Is this a cat or a bird? Well, that's different, because, all of the training data, right? You can just give it more training data and it'll be more accurate, because it's somewhat deterministic in the sense that if you give it enough cat pictures, it's going to get really good at predicting cat pictures, right? For something like spend, or something where you're dealing with real world data, right? You don't have the data to train the model. So this is, sometimes this is why I said, these are some of the, hardest problems to solve, is real world problems. Like something like, is Jason going to buy ice cream on Friday? I don't know. I would need to know the data. I would need to know, does he like ice cream, right? How many times has he bought ice cream in the past, right? I would need to know all this data. So without knowing any of that data, that problem is the same thing as saying, okay, predict the stock market, or predict, gas prices, right? Now, you can make a steady state solution, but when something like COVID hits, something like that, obviously you can't predict it, right? So you can predict the stock market when nothing's happening. But then if something happens, then everything goes crazy, right? So this is what we call a steady state solution, meaning when there's no sort of nothing bothering the market. It's just sort of moving like this. Well, sure, you can get some kind of prediction out, but the minute something happens, like all of a sudden Dow Jones has dropped, right? You don't know why that's going to happen. That kind of stuff can't be predicted. So ultimately, it's useless, right? It's only useful when nothing is going on and the stock market's just kind of not really moving, and it's just sort of same thing with this kind of stuff with the gas prices as well. So those are some of the hardest problems to solve. So you can't predict for nonlinearity, right? You can't really, because you have no training data, you don't know what that's like. You can't compensate that in the model. Okay, so linearity discussion, I think this is important. So first, let's look at linear versus nonlinear. So most functional engineering and scientific results work on the assumption of linearity, right? All of electrical engineering, right? Signals communication, right? A lot of those theories they first start with linear solutions. Nonlinearity cannot be fully predicted. So this is what I was alluding to in the beginning, where I said machine learning is not really good when the data is completely nonlinear, because you can't really fit anything to it. You can't fit a function to it, right? Forcing a nonlinear fit will usually result in overfitting, which is what we see in the right? So overfitting is really when you try to fit some kind of function or curve to every single data point. Now, when this happens, what will happen is when you have new data, the model won't know what to do, because it's basically memorized that curve right there. And that's all it's done. So it's overfitting, right? This is when we say it's overfitting. So if you try to force it too much, it will basically just overfit to some thing that this may not be the underlying function, right? Simply overfit. So machine learning is not really good at predicting nonlinearity. Now, I'm not saying it can't be done at all, but it's just not good in that space. Most of the problems, like I said, has to have some kind of linear correlation. Okay. Let's see. I have to move this here. So you have your linear function, nonlinear function. Okay. Linearity discussion 2, curve fitting at best. So I'm sure you're thinking, what about nonlinear correlation and curve fitting, right? So real world target variables rarely follow known functions, right? I've only seen something like this in maybe like engineering, to where the notion of curve fitting is that if you look at the graph on the right, that's fit to like a parabola, right? So if you have some kind of phenomenon that follows exactly that, you can say, oh, wait, that just looks like this function, right? So in real world, you're almost never going to get something like that. I've seen something like this in engineering only because it's like you're looking at putting heat, you're trying to heat up a piece of metal and then it cools off or something like that, something to where some kind of industrial, process that goes through some kind of physics equation, right? Something like this, to where, so in the real world, you're not going to see a curve like this. If the function is known, well, you don't need machine learning then, because the whole point of machine learning is basically you're trying to, because the function is unknown, right? It's a black box. You have some input, you have some output. You're trying to guess what that function is. So if it's already known, there's no need for machine learning. You could just approximate this with whatever function. So in instances like that, statistical nonlinear estimators may actually be better. So machine learning is not the only solution in data science. So that last point is worth mentioning again, because data science is, it is sort of a space where there's a lot of solutions, right? Sometimes maybe you have to use deep learning. Sometimes you have to use machine learning, but sometimes maybe just a statistical model will work. So you have to think about it as, it's not going to be machine learning is not going to be the solution all the time, right? It may be too robust. It may be, have too much overhead. So if you can do it simpler, lean and mean, that is the solution. So the most important solution, the best solution, is usually the most elegant solution, which is usually simpler, right? So like I said, curve fitting is good, but you're not really going to see a lot of phenomena. Typically, you'll just fit something to like an exponential function, right? Or something like this, parabola, or, and there aren't too many options like that usually. So machine learning and deep learning solutions may not be trusted. So we talked about how machine learning is really functional approximation, right? So some managers may not like a black box approach. So black box meaning that if you remember from calculus, right? Function is like a black box where you put something in, right? And then it gets modified and then it gets, output. And you don't know what that process is in the middle. Now, if you know f of x, then you don't need machine learning. So machine learning is really what we call function approximation. But machine learning won't tell you what the exact function is. So it's kind of a black box, right? Some people, some managers, they don't like that. So your solution might be questioned because they're like, well, it works, but we don't really know how it works. We can't really describe it mathematically. So machine learning and deep learning are both black box approaches. Some people won't accept a solution they don't understand. So generally, machine learning and deep learning offers no explainability other than the technical aspects, which are too complex for the layman, right? So I could tell you how it's doing it, but then you can't easily look under the hood. Model is accurate, but cannot be explained a lot of times, right? You know that, for example, deep learning, the best you can do is you can say, okay, I ran it through a deep learning model and these are the results. The accuracy is high. Well, how is it doing it? Now, your manager doesn't want to hear, okay, I use a neural network here and this is connecting to this. He's going to be like, oh, what are you talking about, right? So uh, since it's opaque, right, people might not, sometimes machine learning and deep learning uh, are not trusted because they can't, like I said, they can't really look under the hood and explain it. So you simply just have faith in it, right? And some people have trouble doing that. So Gen AI and large language models are not really helping in this. I would say Gen AI and large language models add more snake oil nonsense to the mix. So there's a huge debate on this. If you follow a lot of LinkedIn articles, you can see there's a huge culture that's basically calling out large language models for what it is. It's that it's not really intelligent, it's not sentient, but we're being sold that it is. So AI is a buzzword today that everybody, you know, thinks that, oh, wait, ChatGPT, that's artificial intelligence. And everything we do, like machine learning, deep learning, that's all kind of, gets kind of, bunched in with that. So Gen AI uses training data that is copyrighted. So that's a huge debate. So what they do is that, for example, ChatGPT is trained on the entire internet, right? So did they get permission to use this data? No. I mean, so when Gen AI, when you use it for images, right, and you're wondering, wait, how does it, if I just say, bear riding a bicycle, right? It's able to produce that image. Where's it getting it from, right? So it's basically taking copyrighted images from the internet, and that's a huge debate, right? People like Shutterstock, these image places that have all these images, they're getting ready to sue OpenAI and other LLM people saying that, well, you can't just we have that stuff for licensing, right? Where did you get this image from? And it's really hard. The ultimate joke for large language models is that you ask them what their training data is and they don't know, or they won't share that with you. So that's a huge debate right now. So when large language models don't know, they hallucinate. So hallucination means providing wrong data, right? So one of the key things that large language models do is that they can take, like, for example, an essay, and then it can give you, okay, what is this about? And it can tell you, right? It can take some kind of, a large document and then just tell you, this is what this is about. These are the key points. So sometimes it gets it wrong. A lot of times when it doesn't know, it just tends to hallucinate. So there's a lot of examples on this online that I urge you to check out. And then sometimes it will just make up stuff like, if it's, for example, if it's a story that's like, this person went to the store and this person came back from the store and this person took the car out, right? ABC, it will wrongly infer that, something else that's not really even true. That when you read it, it doesn't even make sense. And that's actually wrong data. It's misleading. So you can't really rely on large language models because they tend to hallucinate. And they're trying to come up with, things to fix that, but, nothing's really working because it's not sentient. It's not conscious. It's just basically regurgitating training data, right? So the world is reacting to Gen AI as if all AI equals Gen AI. And that puts us in a bad spot because a lot of people think Gen AI is nonsense. So this sort of reiterates to the fact that, oh, wait, machine learning is black box again. Deep learning is black box again, right? I don't know what's going on in there, right? So So managers might not want to, adopt that solution. So AI in general is getting a bad reputation, I would say, due to Gen AI, right? Because things like, well, where are you getting the training data from? How do you deal with hallucinations? So these things, are basically being brought to light now. Whereas before, people didn't really ask questions about it because they didn't know. Now that OpenAI is making it, made it pretty much, a world affair. Now everybody's, on to, oh, wait, what is your training data again? What does this do? This is a black box. I don't know what's going on. How can I explain it to somebody, right? Other than we put it through machine learning and these are the solutions. And you just have to have faith that technique works, right? So the entire world, I would say, has been duped to believe that large language models are intelligent when large language models are simply regurgitating training data. So they've sort of oversold this and then said that, oh, wait, AI is here, right? AI is here, AI can do anything. When the practitioners of AI are calling this out, basically, all day long on things like platforms like LinkedIn, right? So in the truest sense, LLMs are kind of overfitting to the training data, right? Remember how I showed you that slide where I said, if you overfit to the training data, then you can't really, when new data comes in, your predictions will be bad because you've just memorized that's exactly what's happening here. So what it's done, it's basically memorized basically the entire internet or portions of the internet. When you ask it to write something, it's basically just going to take lines here and there that have already been, so it's kind of plagiarizing data from all over the place, right? And when you give it a task that it's never seen before, it doesn't know what to do. So for example, ChatGPT can write code, right? Supposedly, and then it can solve computer science problems like like program problems, right? But that's only because it's been trained on the entire internet. So if you say write me a program that calculates greatest common factor given these two numbers, right? It might do it because it's just looking at some solution that's already there, right? And it's just regurgitating that. Now, if you give it a problem that it's never seen before, it won't know what to do. So a lot of people have tested this. Like I said, it's not good with basically new data that it's never seen before. So, and that is the definition of being sentient, right? It's not that you're just, regurgitating data. So it's really overfitting to the training data. And then the general, public, they don't really understand this. So the cost of training large language models, the carbon footprint outweighs its ROI. So that is a very important thing. This harkens back to that same thing I talked about, to where any solution in data science, right, has to be doable, right? You can come up with a crazy model that hogs all the resources because it's cool to do, but then it's not practical and you can't put it into, production, right? When you put it into production, it's got to be, lightweight, do the job with less resources as possible, right? For example, if you're deploying a machine learning model, you don't need to deploy it on, Amazon Cloud Services if maybe 50 people are going to use it. When would you put it to the cloud? When maybe you have 100,000 people using it, right, in like a major website or something like that. So if 10 to 50 people are using it, right, you don't need to go to the cloud. You may have other solutions, right? So that's what we're talking about, is that you don't want to kill a fly with a jackhammer, so to speak. And that is a very important thing. Like I said, how computationally expensive is this algorithm? That is a very important question. Okay, I think we're almost to the end here. All right, so this is a very important slide. This is the one I talked about with the managers. So managers don't understand. A lot of times they give you pie in the sky problems. So a pie in the sky problem is a problem that can't be solved with the resources given. And managers or management staff might think that, oh, wait, machine learning can do everything, right? It can do anything. Or same kind of thing with large language models. Oh, wait, I'll just feed it my company document and it'll just summarize it for me. Well, it may summarize it wrong. So what is the cost of that, right? So, but they don't understand this because they're not technical staff. So people who don't understand machine learning will insist you solve the problem and, eventually waste time. So some pie in the sky problems include things like, now this problem was actually given to me, the first one in one of my jobs, where I was told, reverse engineer Google's bidding algorithm so we don't have to pay them as much. So And I immediately knew that this is not going to work. So I said, this is a dumb problem. This is not worth solving. But I had to try and then show that it couldn't be solved just to satisfy the manager. So this is the sort of thing that you're going to get in that it's common sense that one data scientist isn't going to be able to reverse engineer Google's thousands of data scientists that they've carefully done. But this is the kind of problems that you're going to get. You'll run into problems like this. This is what I call pie in the sky problems, right? Predict the stock market, predict the price of gas, or problems similar to this, right? Problems that are similar to this in this kind of nonlinear space, right? Or the proverbial, we have a database full of data, do something, predict something, right? You'll get this because they don't have any defined problems for you to solve, right? They brought you on just because it's nice to have, right? Just so that they can say to their clients, oh, we have a data scientist on staff, right? And they really don't have any problems to solve. So one of the key things that, that I do is in an interview is I might ask, what kind of projects do you have that the person that's going to get this job is going to do? So you have a scope of what kind of projects that you're going to be given, right? So, or predict an outcome from a nonlinear problem space that has no correlation with any features, right? So if the features aren't correlated to the target variable, right, you really have no problem to solve because there's no correlation there. Machine learning algorithms isn't going to pick anything up, right? So, and that is, a key thing to where this is like saying, based on one presidential win, right, use that data to predict who's going to be the next president, who's going to win, right? And it's really not enough data. You can't really do anything with it. This is similar to that, to where it's like, there's no correlation between, one president winning for one reason and whatever the market may be today, right? A president might win today because of some other reason, so things like that, I would say, that aren't really correlated. So the point here is correlation, right? So if there's no correlation between the two, right, machine learning is probably not going to, it's usually going to return back like maybe 50% accuracy. And that's basically at that point, it's a coin toss, right? So if you can't do it, they're going to say you're a bad data scientist. So they're going to think that, oh, wait, this guy's not smart enough. Where the truth is, these problems aren't articulated well, and these aren't really solvable problems. So you have to be given a solvable problem. So this is a very important point here, is that when you're in college, a lot of those problems are actually solvable problems on purpose. Because if they gave you real world nonlinear problems, right, no one would be able to solve it. So in college, you think, wow, I can do all this stuff. Maybe you downloaded some data sets in Python and, you're looking at the housing price data, or, you're looking at idealized data where everything just works out fine. So when you get to the actual job, none of the data is going to look like that, or none of the models is going to look like that. Like I said, you'll probably come back with something like 70% accuracy if you're lucky. And then, whatever else you can do in feature engineering to try to get more accuracy. A lot of the times you'll come back with 55% accuracy, which is not enough for problems like this, right? So you will solve problems like this, I think. Or you'll be asked to, and then you'll be basically say, wait, I came back with 55% accuracy. This can't really be solved. And they're not going to trust you until you actually run it. And that's the sad part, because you're wasting time, right? You're wasting time with unsolvable problems. So you should develop an acumen for problems that can't be solved. So if there's no correlation, if it's highly nonlinear, it's probably not going to be, solved, or the accuracy is so low that it can't be used, right? So if you come back with 60% accuracy, is that useful? I don't know, depends on the manager. Most managers won't accept anything less than at least 70%. Okay, so I think we're at the end of the slide here. So this is super important here. So technology hype curve, AI, large language models, Gen AI, machine learning, deep learning, right? So anytime you have technology, there's a hype curve like this, where the product is oversold, right? So there's an innovation or trigger, and then immediately what happens is there's a peak of inflated expectations. So this has basically happened with everything. Today, this is happening with large language models, right? It happened with machine learning, right? So, and then there's a trough of disillusionment. So the public finds out that, oh, wait, it can't really solve everything, right? And then we call there's a slope of enlightenment to where we understand that it can't solve everything. And then we kind of make progress slowly, and then we kind of understand the use cases in which it could be used. We understand that it's limited use cases. And then there's a plateau of productivity because we understand where to use it and where not to use it. So, for example, machine learning went through this. When machine learning first came, now remember, machine learning is really just, all it does is basically offer more accuracy, higher accuracy over statistical methods, over traditional statistical methods using computer science methods, which is computational. So I always say machine learning is computational, whereas like statistics is more of a statistical model. So really, for as far as prediction is concerned, that's all it's done. So we have ensemble models, we have different models. So when machine learning first came on board, people thought, oh wait, this is like magic. So it can do anything. As we discussed many times in this presentation, if there's no correlation in the data to the target variable, you're not going to have anything. So people thought that they could just put whatever data in there, and machine learning would basically spit out something that's like useful. And that was dubbed, oh, this is the new gold, right? So you'll hear fear mongering, things like, if you're not using machine learning and AI, right, you're being left behind by your competitor. So when you hear something like that, that's really a salesperson using a fear mongering tactic, right? So with machine learning, there's innovation, and then the peak of inflated expectations, right? Everybody thought, oh wait, this is it. All we have to do is put machine learning into it. This is going to give us like 80-90% accuracy. And then of course that's always followed by a trough of disillusionment, saying, oh wait, machine learning can't solve all the problems. Just like we talked about here, right? It's not really good for nonlinear problems. There has to be kind of correlation there, or else it can't really solve it. Now we sort of understand, oh, wait, it can't solve everything. You have to have the right use case for it. And then you have the plateau of productivity, right? Deep learning, the same thing. People thought, oh, wait, deep learning, this is it, right? Deep learning will basically take its own features. So deep learning went through the same kind of cycle to where, inflated expectations. And then now we understand that, oh, wait, deep learning is usually overkill for most things. It takes a lot of, training time. It takes a lot of data to train. And it's really helpful in things like computer vision, pattern detection, right? But you may not want to use deep learning for like everyday modeling, right? Usually ensemble models work best. So once we understand the use cases, now there's a plateau of productivity. With large language models, we're actually at the peak we're climbing that peak of inflated expectations, because people think that large language models will basically, do anything, right? And they don't understand that, oh, wait, a hallucination could basically kill the whole thing, because what's the point if it's giving you 80% right information, but then the 20% that's wrong is so wrong that if you take a decision based on it, it's going to be catastrophic. So what good is that technology, right? So we're actually climbing that curve right now, and probably within this year, or maybe next year, people will sort of look back and then say, oh, wait, it's not the latest and greatest thing, right? Or it's still not there yet, right? So I read an essay that was, so now, large language models can basically just write essays and things like that, right? That people can turn in, kids can turn into their school. So if you just say, write me an essay on trees, right? It will write you an essay on trees. That's pretty convincing, right? So I actually looked at a human essay on a subject versus an essay generated by large language models. And I read both of them. And any human being can tell that this was not written by a human being, the one that's written by a large language model, because it's basically just plagiarizing stuff from different places, and it's almost too perfect, right? So it's not something that's really useful. I can find some uses in maybe things like, the medical industry, to where, they have to send a lot of notifications about prescriptions and things like that. But right now it's being oversold. And what bothers me most is that there's already jobs created for Gen AI, Gen AI engineer, Gen AI specialist, where a lot of these things without prompting, right? It's really limited. So you still have to prompt it carefully, right? Now they have prompt engineers. That's a whole job, just to prompt it carefully to give it something. Like if you look at image generation, I played around with image generation. You have to keep prompting it for the right one till you get the image that you want. So anybody in marketing that's going to use image generation might get frustrated. It's a hit or miss. So you have to keep saying, for example, give me trees mounted in a house. And he might give you a picture and you go, I don't like that. And you got to keep doing it. You got to keep doing it till you get the right one. So after maybe about 20 times you do it, you're kind of like, okay, this is the closest one that looks sort of like what I asked. So I might take this. So how, useful is that, right? I think for sort of a blanket marketing campaign, maybe Gen AI image generation is useful, but language models have a long way to go. Same sort of thing to where it's not really going to be useful if it's wrong, right? So right now, like I said, with large language models, it's basically at the peak of inflated expectations. And then with this essay, anyone can clearly tell that this is not good. And, teachers are basically saying, do not use ChatGPT to turn in your, assignments because it's going to be too obvious, right? The essay written by the human being had heart in it. This one didn't. This one looked like it just took like a bunch of facts from, different places, put it all together in a convincing way, but it's too perfect. It's almost like no one's going to believe that maybe like a high school kid wrote that, right? So that in itself will get them caught. Nothing more than that. It's like you did this. This looks almost too perfect, right? So it's lacking the human aspect of it. So it's probably going to go through the trough of the disillusionment pretty soon, and then they're going to find the correct use cases for it to use. So none of these solutions are going to be solutions for everything, right? Nothing is going to be one size fits all. To find some kind of generalized artificial intelligence solution, it's going to be a long way because right now AI is still an emulation. So the word emulation is really important. Emulation means that it's basically just mimicking, right? It's basically just mimicking a human being to the point where it's convincing. So it's not really thinking, it's not really feeling. How can it when it's basically a statistical model? Because we don't think like large language models. As I'm speaking, right? I didn't say I'm going to make up a sentence. I has a probability of 50%. Am is going to have a probability of 70%. Going is going to have a probability of 80%. That's not how we think, right? The words just flow out. That's what large language models are doing. It's just basically, a statistical model to where each word is a probability, but it's gotten really good at guessing. So that's all it's done. So it's gotten really good at guessing. When you have to guess what the next word is, how can it actually understand what's going on? So it may seem like it's understand what's going on because it's just the emulation, but you can kind of, catch it really easily, like many people have done on LinkedIn, where if you ask it a real question, it won't know what to do, right? So I think generalized artificial intelligence is still, a long way, and there are other techniques that people are using other than ChatGPT type material that uses kind of reinforcement learning, that uses the attention model, right? Like symbolic learning, right? That seems to be more, gaining more traction than something like this, to where it's just a statistical model that just, if the probability of the next sentence or the next word is wrong, you're going to get the wrong results, right? So anyway, guys, that is my presentation. And I want to thank you. Thank you for inviting me to your company. And I have my LinkedIn information, and then I will also be posting this on YouTube. So I have a couple of other projects on YouTube about reinforcement learning and some other projects that you might be interested in. And I will upload more videos on that. And I will share this video on YouTube and LinkedIn. And thank you. Have a great day.